Good work. All right, starting with the structure on the top left, we have to remember the priority of our different groups in order to decide where to start numbering. We said earlier in the semester that the priority has alcohols at the top. So find the longest carbon chain that includes the highest priority functional group. Alcohol, then a tie between alkene and alkyne, whichever one can get the lowest priority, the lowest locant. Then alkyl groups and halogen groups. So find the longest carbon chain, including the highest priority group, and number in such a way that the highest priority functional group gets the lowest locant set possible. So those would be the 2 points. This is priority for parent chain and priority for lowest locant. That makes sense, right? I think I've said this before, but it's actually not well illustrated in any of these examples. You don't necessarily find the longest carbon chain. You find the longest carbon chain that includes the highest priority functional group. I don't think I'm going to give this to you guys on this exam, so I'll give you one excerpt that proves this. Cyclohexane with a 2-carbon chain coming off of it and an alcohol on that 2-carbon chain. What is the longest carbon chain that includes the highest priority functional group? Ethyl. It's an ethanol chain. So this compound is 1-cyclohexyl ethanol, or 1-cyclohexyl 1-ethanol. We're not going with the longest possible carbon chain because the 6-membered ring doesn't include the highest priority functional group. We're doing the longest parent, or the biggest parent chain that includes the alcohol. None of these examples illustrated that very well.
Phenol is just oh my gosh.
An aromatic ring.
Yeah, an aromatic ring. So that one would technically still follow that, where like the aromatic ring, I know it's its own functional group.
Yeah, correct. The aromatic ring,
has 6 carbons.
it doesn't fall well into a lot of the priority listings. It's actually unclear to me whether the aromatic ring is higher priority or lower than alkane. So, but you don't have to know how to name aromatic rings. That shows up in OCHEM 2.
I wasn't sure if that would be another one that was similar to.
Correct. Yeah, actually, if you did make this an aromatic ring, still ethanol would be the parent chain.
Well, yeah.
All right, so with this top one, I can always start anywhere in a ring. I'll start in a ring where there's a substituent. And in this case, I might be tempted to just start where there are 2 substituents, but that is not how you should approach it. You should start where the alcohol is, because I'm looking to give the lowest locant set to the alcohol. Coincidentally, that is where the most substituents are. Coincidentally. Deal? All right, so I start numbering so that the alcohol can have its lowest locant. Because I'm on a ring, I can start anywhere, and I have to start to give the alcohol its lowest locant. I don't actually need the 1 here. If I don't want it, it is assumed the alcohol is at position 1, because where else would it go? I'm looking to minimize its locant. But it's great to have it in there. 4-bromo, 1-methyl, hexane, 1-ol, 4-bromo, 1-methyl, 1-hexanol. or 4-bromo 1-methyl hexanol. No, sorry.
I don't know, yeah, I'm sorry.
Yeah, I was not processing that fast enough. Thank you. Cyclohexanol. Was anybody else going to say that eventually? Good, thanks. I missed that. Cyclohexanol. Okay, 5,5-dichloro 2-pentanol. This time, there is absolutely no way that I can ignore the locant for the alcohol, because on a linear chain, it can be in a lot of different positions. Even if it's on the end carbon of a chain, I have to say 1-all. On linear chains, locants are always required. In rings, that highest priority group doesn't require its locant. 5,5-dichloro 2-pentanol, or like we saw over here, 5,5-dichloro pentane 2-all. I described the suffix for the alcohol as a suffix stopper. I'm essentially saying pentane with an E at the end, but I'm dropping the E and stoppering the suffix ane with this stopper all to indicate the alcohol. I actually need essentially two suffixes. I need a hydrocarbon suffix, and I need the suffix for the alcohol. By the way, alcohols can also show up in a prefix. They're given the prefix hydroxy. But if they're the highest priority group, it's more common to see it represented in the suffix. 4-methyl cyclopent 3-ene 1,2-all.
Sorry, going back to the one before, so either of those are acceptable?
Correct. Actually, this is what IUPAC wants. IUPAC says put the locant directly before the description of the functional group. But nobody cares, so they just have historically always brought it in front of the root.
So either?
Either will be accepted, yeah. But I want you to see both. Great job. First, start at one of the alcohol positions. That means I could start at the left and go to the right, or start on the right and go to the left, because I don't want to just get the lowest locant set for one of the alcohols. I want the lowest locant set for both of the alcohols. So I'm going to number from one of them to the other. So why can we decide whether to start on the right and go counterclockwise or start on the left and go clockwise? After I get the lowest locant set for the alcohols, then I need to get the lowest locant set for the alkene as well. Either way, my alcohols are going to have priority 1 and 2. I'm sorry, locant 1 and 2, whether I start on the left and go clockwise or start on the right and go counterclockwise. So after those are already established to be locants 1 and 2, then I aim for the lowest locant set of the alkene. By the way, these are the only functional groups that you have to name on the final. So it's not a long list of rules for priority. So if I number counterclockwise, I get to the alkene at 3. If I number clockwise, I get to the alkene at 4. So I'm going to number it so that the alkene has its lowest locant after the two alcohols have their lowest locants. But I have to describe how many alcohols are present. Just like we say dichloro, or like we say dimethyl, we have to say diol. So this becomes 3-ene 1,2-diol. And this is a part of the nomenclature. If I ask you to write out the name, I'm not going to grade so heavily on this. But IUPAC nomenclature doesn't like to butt up consonants or vowels, except I guess in the case of like the YL with the start of a root. So we dropped that E to make space for OL so that we didn't have enol with an E and an O next to each other. We dropped the E. But now we don't want to have N-diol, so we put the E back in. Silly, right? Which is actually why in this example, you were given hexane hexol. The hex is the multiplier for the alcohol. And because I don't want to have two consonants butted up against each other, the E that was dropped originally comes back in. I did not make the rules. And in my opinion, it's one of the least important rules, so I'm hardly even going to enforce it. Did you have a question on that?
I was just gonna, like, if we did that on the final, would we get points off?
No. If you have the right suffixes, I care more about the multiplier than I do about adding the E back in. And you can see why we need the multiplier, because we always have to define how many of those groups we have. Okay, from our drawings, 1, 2, 3, 4, 5, 6, hexane, hexol. So I've got a 6-carbon chain, and I have an alcohol at each of my positions. Notice how the name was not hexane, hexol, but the name described the locant of every single alcohol, because there are a lot of structural isomers of hexane, hexol. I could have had 3 alcohols on this methyl carbon, 3 alcohols on this methyl carbon. That's technically a structural isomer of hexane, hexol. That's just 1,1,1,6,6,6 hexane, hexol. So the locants matter. For phenyl but 3-ine 2-ol. This is an instance that really emphasizes why IUPAC wants the locant directly before the functional group that it's describing. I would not be able to take both of these locants, which are describing different functional groups, and bring them both in front of the root, because then it would be confusing which group I'm describing at which position. Is the alkyne starting at 3, or is the alkyne starting at 2, right? So when we put the locants directly in front of the thing that designates the functional group, it makes it much easier to figure out where that functional group is the carbon chain is. There is one change that you can make. You can take whatever the first locant is, and you can bring that first locant out front. Like here, the first locant was 2-ol, and so we could bring that out front. Here, the first locant is the 3-ine, so we technically could bring that out front, 3-butyne 2-ol. But in my opinion, it's just better to keep the locant right next to what it's describing. 1, 2 alcohol, 3, 4. That's an internal alkyne, because then it's bonded right to the benzene, the aromatic ring. Okay. So nomenclature. Think about the priority. Find the parent chain with that priority in mind. Establish a locant set with that priority in mind. And make sure that you list multipliers and locants. Make sure that your names are listed alphabetically. How do you guys feel on nomenclature? Better than other topics? Good. All right. We have a few more reactions to learn today. So our next reaction diagram here, reactions with alcohols. You will notice that these reactions are substitution or elimination reactions. Obviously, alcohols don't have pi bonds for us to do addition across. And I'm giving you a chiral alcohol. so that you can see what happens with certain reactions in regard to stereochemistry. Our first reaction is elimination. We've just learned about elimination. For instance, if I had 2-bromobutane instead of 2-butanol, I could react this with a small, strong base. This is a strong nucleophile, strong base. And if I expose it to heat, it will react to give the most stable alkene, which in this case is the trans 2-butene. I could also react this with tert-butoxide to get the anti-Zaitsev alkene, the less stable alkene, because my big bulky base can't get to the sterically hindered secondary carbon and takes the lower energy route to go to the less sterically hindered primary carbon. With alcohols, we can't use bases at all. If an alcohol was exposed to something like methoxide or tert-butoxide, I just establish an equilibrium. It's just two alcohols deprotonating each other. Not great. Here, the most acidic hydrogen is only on a carbon. So the base has one place to choose to eliminate. The base has one place to deprotonate, a carbon. But here, the most acidic hydrogen is attached to the oxygen. Far more acidic than a hydrogen connected to carbon. Why? Electronegativity. Carbon and oxygen are in the same row, so Cario says the more electronegative will be more acidic. So I can't run elimination of alcohols using a base. How do I eliminate an alcohol? You guys did this in lab. We add acid. And there's a lot of different ways that we can communicate acid. Sometimes we communicate acid by just saying H+. But a lot of times you will see the acid listed here specifically as sulfuric acid. And this is technically an equilibrium reaction. I don't know why I say technically. I'm not showing it in equilibrium, but this reaction kicks off a molecule of water. So this is referred to as acid catalyzed dehydration. But back in section 7, right after the midterm, or rather right before the unit test, we learned that alkenes react with water and acid to do acid-catalyzed hydration. So we're in equilibrium between acid-catalyzed dehydration and acid-catalyzed hydration. Either reaction I run has the chance of reversing itself. In lab, you guys got around to this by distilling the product, taking the alkene and the water away from the acid catalyst so that they could not reverse the reaction. And we could do a similar thing if we were trying to do the opposite. If we were trying to do acid-catalyzed hydration, we could try to separate the alcohol as soon as it formed to make sure we don't reverse the reaction. Okay, to the right, what type of reaction do we see here? Substitution. Specifically, a sort of chiral substitution, because my wedged alcohol has been replaced by a dash chlorine. That reminds you of what type of substitution? SN1 or SN2? SN2 results in that inversion of stereochemistry. SN2 has a backside attack. The reagent that we use here is thionyl chloride. You guys might remember during the first week of class, I had you draw out the Lewis structure of thionyl chloride. It's a hypervalent sulfur. It has 10 electrons around it. The mechanism is interesting, and some textbooks will report that you need thionyl chloride plus an additional molecule, pyridine. Some will say that you don't need it. Some will say that with pyridine versus without leads to differences in stereochemistry. You're going to see it from me as just thionyl chloride. We're not going to look at the mechanism, but the mechanism is not entirely hard. It simply has this one step where the oxygen is bound to the sulfur after a chlorine has been kicked off, and that chloride substitutes that group, backside attack. We see a very similar thing in the next reaction. Instead of a chlorine, what do we have? A bromine. And the reagent that we need here is phosphorus tribromide, PBr3. Once again, the alcohol will bind with the phosphorus, kicking off a bromide, allowing bromide to do a backside attack. Substitution of alcohols into alkyl halides. What would be the usefulness of that? Well, for one, my alcohol is always eliminated by Zaitsev elimination. It always forms the most stable alkene. This is actually an E1 elimination every time. And E1 will always give the most stable alkene, which means I can never take my alcohol to a less substituted alkene. I can't control the regiochemistry of my dehydration reaction. So I can substitute the alcohol for an alkyl halide, which can be regio-controlled, leading to a multi-step synthesis type setup. Okay, to the bottom left, show the alcohol being converted into a generic halide. And talk to me about the stereochemistry. Just like with SN1, this is not inversion or retention. It's inversion and retention. I'm getting a mixture of both the R and the S chirality centers, which means that this does not do SN2, this does SN1. And the reagent that we need is HX. That could be HCl, HBr, HI. So this leads to one important distinction with the acid-catalyzed dehydration. It's not just any acid. If you try to run acid-catalyzed dehydration using hydrochloric acid in the lab, you won't eliminate. You'll end up substituting. So there's a difference between the conjugate bases. When sulfuric acid acts as an acid, it forms bisulfate or hydrogen sulfate, and this is essentially not a nucleophile. We could say it's a very bad nucleophile. It's so bad, it doesn't behave as a nucleophile. But when hydrochloric acid is present, its conjugate base is chloride, which is a poor nucleophile, but does act as a nucleophile. Or similarly, hydrobromic acid conjugate base is bromide, which is a nucleophile and a strong nucleophile. SN1 in acidic conditions with a nucleophilic acid versus E1, alcohol in acidic conditions with a non-nucleophilic acid. Last one. Alcohol to OTS. What do you notice about the stereochemistry? It's conserved, it's retained. The reagent that we need here is called tosyl chloride. As opposed to thionyl chloride. And you'll notice that the Cl is gone. So the substitution that's happening here is oxygen substituting chlorine on this tosyl group. In fact, I want to highlight that this original oxygen of the alcohol is the oxygen present in this new group, this tosylate group. And do you guys remember the way I told you to think about this tosylate group? It's a pseudohalogen. Think of it like a halogen. Now that I've made this halogen, I can do different types of elimination with it and gives me more regio control. But there's a stereochemistry impact. If stereochemistry is important and I need to invert it, thionyl chloride, phosphorus tribromide, they allow me to change my alcohol into a different type of leaving group, and they swap the chemistry, the stereochemistry. If stereochemistry is important and I need to retain it, converting my alcohol into a tosylate allows me to retain the stereochemistry, but still make the oxygen into a good leaving group in these basic conditions. I want you to notice there's no bases introduced here. We can do stuff with acids, and we can do stuff with inorganic reagents, but there's no base because alcohols react with bases by donating their hydrogens. Alcohols and bases don't do chemistry other than acid-base chemistry. All right, let's look at one of these transformations in a multi-step synthesis perspective. I also want to highlight something I mentioned last class about the stereo-specific nature of E2. You guys are okay if I clear this? All right, so we're going to start with this cyclic structure. I have an alcohol, which can be eliminated by acid-catalyzed dehydration. Acid-catalyzed dehydration is an E1 mechanism, which means there will be what type of intermediate formed? Carbocation forms. This one does not form in quite the same way. First, the acid protonates the alcohol and essentially forms water bonded onto the alcohol. And then water breaks off, just like our halogens do. So a carbocation intermediate forms. And it could rearrange to either position. Let's assume it doesn't rearrange. Or even if it does rearrange, let's look at a selection of the structures that it could form. If the alcohol forms an alkene, if it goes through elimination, and forms an alkene between the tertiary carbon on the left and where the carbocation forms, it forms a tri-substituted tri-substituted alkene. If the elimination runs between the carbocation position and the tertiary carbon on the right, I drew that as a wedge. It's supposed to be a dash. Do you guys remember what TBU stands for? Tert-butyl, yeah. I form a tri-substituted alkene. Which one is more stable, a tri-substituted alkene or a tri-substituted alkene? Equally stable. So I get a mixture of products because the stability of the products formed is equivalent to each other. I might not like that. I might want one alkene or the other. So how can I control which alkenes I get? Let's take thionyl chloride and let's convert this alcohol into an alkyl halide. It might feel like nothing has changed. I can still form a tri-substituted alkene towards the methyl. I can still form a tri-substituted alkene towards the tert-butyl. The problem was the alcohol could only be eliminated by E1. The alkyl halide can also go through E1 elimination, but using a strong base, I can make the alkyl halide go through E2 elimination. And E2 elimination requires an anti-planar hydrogen, a beta hydrogen. Here's my alpha carbon. Why? Is that obvious to you that this can be alpha? It's got the leaving group, so it's a carbon of interest. It's our alpha carbon. And the beta carbon is adjacent to it. I've got a beta carbon on the left, a beta carbon on the right. Both of those carbons have hydrogens. Here, the beta hydrogen is dashed. How do I know that? Tert-butyl's wedged. There's only one stereo position left, dashed. Is a dashed hydrogen anti to a dashed chlorine? No, and we can go back to Unit 2 when we were doing stereochemistry, conformations, Newman projections, and we can prove that when two things are dashed, they're on the same face. They're both down. They'll never be anti to each other. On the right-hand side, I have a beta hydrogen, and it's wedged. Is a wedged beta hydrogen anti to a dashed chlorine? Yeah. So if I run E2, which does not have a carbocation, E2 requires that the leaving group and the adjacent hydrogen are anti to each other and in the same plane. If I run E2, how many of these hydrogens can I actually remove? 0, 1, or both? Just one. Which one, Jordan? The anti one on the right. So let's introduce a small base, sodium hydroxide. It is stereoselective which hydrogen it's allowed to eliminate. I didn't really mean to get rid of my ME, but sometimes just forget to draw the ME when that just adds more work as opposed to just drawing a line. Okay, I would like for you guys to derive a way in 2 steps to isolate the other alkene. Might help to think about what the stereochemistry would need to look like immediately before this elimination. Perfect.
Question. So once it becomes this, say, pseudo halogen,
Mm-hmm.
there's no need to put like another halogen on there.
No. Because if a halogen would leave in that situation,
Yeah.
then this group will leave in that situation.
Okay.
Did you figure it out?
No. How do we know that that's like stereoselective? Like,
How do we know what is? E2?
oh, is that what you were saying? Or that reactant?
Well, that product?
Like the NaOH, that's stereoselective? Or
Yeah,
the type
it
of
is.
reaction we're running is stereoselective?
Both. That reagent, sodium hydroxide, is a strong base, strong nucleophile. So you will only ever see it run SN2 or E2. Sodium hydroxide will never run SN1 or E1. And we know that because of that table we made. But because of that, its elimination is stereoselective, antiplanar. Its substitution is stereospecific. It'll always do inversion of stereochemistry.
So that was an example of E2.
It is an example of E2. And the top is an example of E1. E1 is not stereospecific. It's not stereoselective.
Because you don't know.
Correct. E1 forms a carbocation, and from there, either side is fair game for elimination.
So the carbocation would be on that like alpha carbon, and that's deciding now which way to go.
The top,
Where the OH is.
yeah, the carbocation will form on that top carbon.
Okay.
And to be fair, I didn't mean for this, so I wasn't planning that. To be fair, the carbocation would rearrange. If the carbocation formed here, it would rearrange to either tertiary position. And these are still alkenes that you could form from either tertiary position. I just didn't want to draw 2 extra products. There are other alkenes you could form from those tertiary positions as well, but that was beyond the point. The fact of the matter was the carbocation being flat, achiral, is not stereoselective, and it can eliminate either beta hydrogen. But E2, no carbocation, it has to be anti. If it's not anti, it won't do it. Like here, why didn't it take this hydrogen? Why don't I get that second product? It's not anti. It'll never be anti. It will never go through E2. Okay, did you figure it out?
I think so.
Yeah? What do you think, Christine? Can you figure out what stereochemistry you would need at that alpha position? Even if you're not sure what group is going to be there, can you figure out what the stereochemistry would need to look like in order for it to be stereoselective? Oh, your tert-butyl flipped. Should be wedged still. The problem is, I don't have a reaction that takes my OH to Cl and keeps it wedged. I have a reaction that takes it to Cl but inverts it. But you're right, that's the stereochemistry I would need. So now I just need to find a reaction that will preserve the stereochemistry but make it a better leaving group. Ready? Jordan? What should I introduce? Tosyl chloride converts the alcohol into a tosylate, but does what with its stereochemistry? Preserves it. Exactly. Keeps it the same. Yeah. So the structure is an aromatic ring with a methyl group. That is called toluene. But it also has a sulfonyl group, and toluene sulfonyl becomes tosyl. And then after you get rid of this, and then you bind it to something, well, actually, so the TSCl looks like this. And then we substitute the chlorine with the alcohol's oxygen, and we get the TS group, tosylate group. I've landed on tosylate as my favorite, but there is a whole family of sulfonyl groups. This is TSCl, but there's also MSCl, which is literally just a methyl group. And there's TFCl, which is a trifluoro group. Mesyl chloride, triflyl chloride, and tosyl chloride. And the reason that you would distinguish between them depends on your solubility in lab and your electronics in lab. It really would just, they do the same thing, but they're different. Same thing, but different. Okay. Tosyl chloride doesn't invert, preserves the stereochemistry, retains the stereochemistry, which means that the only anti-hydrogen is now the anti-hydrogen next to the tert-butyl group. What base should I introduce? Tanner? Same base. Why not? Because the same base runs E2. And I want this to be E2 so that it's stereoselective. I do not want it to be E1, which will go in either direction. It is not stereospecific. So I could use sodium hydroxide, sodium methoxide, sodium ethoxide, sodium tert-butoxide even would work here. Things that would not work, water, methanol, ethanol, those are all weak bases that will run E1 rather than E2. Jordan.
Yeah, so we don't want E2 there, or no, we don't want E1 there because it just goes to the most
Correct.
That's what's happening. Okay, can you explain why we chose the, what is that? Something chloride?
Tosyl.
Fossil?
Tosyl chloride.
Fossil chloride?
We chose it because converting an alcohol into a tosylate retains the stereochemistry. And in E2, the stereochemistry dictates which hydrogen I'm allowed to remove. If there are two hydrogens, then it's fine. Either one of them is going to work. But if there's only one hydrogen, it matters its stereochemistry. Kirsten.
So I know NaOH is a strong base, but it would fit the it would better fit the ROH, which is classified on our sheet as a weak base, weak nucleophile.
What better fits ROH? NaOH?
NaOH, because it's
R.
is like the rest. And OH is the alcohol, and it's the only strong base, strong nucleophile that is an alcohol listed, I guess, is O as just, I don't know how to say it, but OH minus.
Are you guys all right if I erase the diagram on the left? You guys got all this?
So I'm just wondering.
You raise a good question that R might be sodium, but I don't want you to think that.
Okay, but then.
Because when we say ROH, we are inferring covalent bonding. R is covalently bonded to O, is covalently bonded to H. If we wanted to imply ionic bonding, we would actually say MOH, M standing for metal.
Okay, so the OH minus is saying that that ion is bonding to Na plus, which
Yep.
is getting that ionic bond.
NaOH,
NaOH is,
if you want to draw the Lewis structure of NaOH, this is what you draw. If you draw the Lewis structure of NaOH like this, you lose points because there is not a covalent bond between them.
thank you.
They are ionically bonded. And I'm sorry that I cut you off while you were still finishing your question, but I just wanted to nip that in the bud. The R should not be considered an ion.
Well, yeah.
But the problem-
appreciate that
The problem is we do say R means the rest. And if the rest is an ion, that is confusing. Yeah. So we should think of R as something covalently bonded, which means I could use NaOH, which is the Na doesn't matter. I could have also used KOH. Those are both sources of OH minus. The cation is a spectator. But I could have used any version of RO minus as well. In fact, I could have used tert butoxide because there's only one hydrogen to go to. Typically, meth oxide, eth oxide, all of those smaller alkoxides, they will go for the most stable alkene. They'll go for the most substituted hydrogen. Tert butoxide goes for the less stable alkene, the less substituted hydrogen. But in this case, there's literally only one hydrogen available. So there is no Zaitsev or anti-Zaitsev product. It is one choice. So we could have actually done anything that is a strong base, but no weak bases. Okay.
I just wanted to clarify, and that's helpful to think about the fact that R is a covalent.
Yeah. Thanks for
Like the ionic bond.
Thanks for bringing that up. Okay, good on alcohols? Layla?
So on the carbon bonds to methyl and the carbon bonds to terpene, those are both tertiary.
Those are both tertiary carbons.
And we're doing E2 elimination.
Here we're running E2.
Yeah.
Here we're running E1,
Right.
which is why we get a mixture of both. E1 is not stereoselective.
So if we use a weak base and a weak nucleophile in E2 reaction on a tertiary carbon,
There is no E2 with a weak base, weak nucleophile.
Oh, okay.
Good question. Tell me more. I'm not sure. We can do E1 with a weak base, weak nucleophile.
So how is NaOH categorized? Is it a
Strong base
strong base?
and strong nucleophile.
Oh, why did I have that wrong? Okay, never mind. I just have my notes wrong.
I think actually I should have maybe given you guys heat here as well, right? We talked about that last class. This is a secondary alkyl halide. So heat will make sure that we don't have any competition between substitution and elimination. It is cumbersome when the same reagent can give multiple different products. Sometimes we clarify that by just saying, show the elimination product. And then you don't have to worry about the substitution. Other times we reinforce the idea of the temperature control. Should we do a break? Okay, 5 minutes. Come back 6:07, 6:08, and we'll dive back in.
So these, I've categorized these as weak bases, weak nucleophiles.
Yeah. This is not hydroxide.
Oh, we're doing this one bonded to.
A cation.
Okay.
Yeah, but this is ROH, not a cation. Or sorry, not an anion.
Okay. How do I differentiate between like NaOH and OH minus? I'm confused.
They're the same.
Okay.
Yeah, in fact, NaOH has a spectator ion that we don't care about. So does potassium hydroxide, just has a spectator ion. So when you see these reagents, you should just think of this.
Okay. If for some reason we wanted to run this here,
If
how would I write that?
well, first you'd have to just pick a carbon chain to call R.
Oh, it's a carbon chain.
So call it methyl,
Okay.
call it ethyl,
Okay,
call it
okay.
isopropyl.
Okay, that's what we were talking about earlier.
Yes.
Okay, that makes sense. Okay, thanks.
Good, you're welcome. Yes.
I have a question. What was the difference? You said that adding the heat on the bottom of that.
So that table that we made said secondary alkyl halide, strong base, strong nucleophile, has competition between SN2 and E2. Heat is a temperature control. If I add heat to a reaction that has competition, it promotes elimination. If I remove heat, if I run it at low temps, it promotes substitution.
Oh, because he's crazy, actually. He's running the singles at 8 a.m. on Saturday, and then ours is at 12.
If I replace the delta with low T, then I would actually expect to see substitution of the alkyl halide rather than elimination of it. And if I didn't specify either, I would predict both are going to show up. I actually would go from this with NaOH and low T back to this. SN2 inverts the stereochemistry, substitutes the alkyl halide for an alcohol. Low temp promotes substitution. High temp promotes elimination. You're welcome. Britton. At the top of the worksheet from our last few classes, and then we categorized them. But I do abbreviate most of them as RO minus. And really the only RO minus that can't be a strong base, strong nuke is when R is tert butyl. Correct. But RO minus could be meth oxide, could be eth oxide, could be isoprop oxide. But when we write them as reagents, you might not see them as the negatively charged oxygen. you'll see it as sodium methoxide. Maybe you'll see it as potassium ethoxide, or potassium tert butoxide, which if you write it the right way, you get T-bu, okay? I had somebody once come up and say, what does okay mean? Good question. Potassium oxide. What? With potassium, it's neutral, but potassium's not doing anything, so I often will just emphasize the thing that's doing something.
Why is it there then?
Well, because of charge balance. It is really hard to find a chemical in a lab that doesn't have a counterbalance in terms of charge. I'm trying to think right now. Never heard of it. Yeah, like you can't go to the lab and just get hydroxide. There's some cation counterbalancing it, whether it's sodium or potassium or ammonium, all balancing. Good question. All right, let's dive back in. I'm excited, are you? These next few reactions are very similar to our typical alkene addition reactions. The problem is they are conjugated dienes. Can anyone remind me what conjugated means? Conjugate your verbs, conjugate your acids and bases. What did you say, Allie? Spanishize them. It means there's some relation. There's a relationship between the dienes, and here the relationship is, starts with an R, resonance. These dienes are in resonance with each other. So we've got this 1,3-butadiene as our starting material, and we're going to consider 3 reactions that we can do here. This is a conjugated diene. You'll notice that it's an uninterrupted series of sp2 atoms. And all of those sp2 atoms have a p orbital on them. I'm not sure I really want to draw it out on top of it. All 4 of those atoms have a p orbital, which means there's an uninterrupted series of p orbitals, which means that they are all sharing a pi bond. Molecular orbital theory describes it and illustrates it better than Lewis structure can. These dienes don't behave exactly like normal alkenes, because the most stable carbocation that they can form is the carbocation that is allylic, meaning adjacent to an alkene. The most stable carbocation it forms is a resonance-stabilized carbocation. But we can control the stability of that carbocation. So first of all, if we look to the right, I show us forming 3-bromo, 1-butene, which is an HX addition reaction. But if you look to the left, we form 1-bromo trans 2-butene. And if you are doing the stoichiometry, that is also an HX addition reaction. So how is it that I can add H and X right next to each other across one of the pi bonds? Or I can add H and X further from each other and kind of consume both pi bonds but relocate one of them to be in the middle. These are structural isomers of each other, and they differ by temperature control. If I add HBr, but I run this at very low temperatures, you know how cold that is? That's so cold that Celsius and Fahrenheit scales came together and met at -40 and then diverged from each other. This is very cold. Essentially what we have here is just enough energy for the molecules to move around and find each other, but not a lot of energy for anything else. We call this a kinetic reaction because it requires only the energy of movement to form the product. A kinetic product. We also refer to this as a 1,2 addition product because the hydrogen and the halogen have formed across atoms 1 and 2. They've added across atoms 1 and 2. Unfortunately, not all 1,2 addition products are the kinetic product, and not all, anyways. If I want the product on the left, I'll run HBr, but I'll provide it with more heat. And in this case, heat might just be room temp. We call this the thermodynamic product. Thermodynamic means heat and change. And I'll be honest, that doesn't always make sense with what the structure is. But we can also refer to this as the 1,4 addition product because I add a hydrogen to atom 1 and the halogen to atom 4. Now I want to take a look at the mechanism for this, just briefly. My alkene serves as a base in the presence of an acid. We've already seen that. The alkene deprotonates the acid and forms the most stable carbocation. In this case, the most stable carbocation is that which is in resonance. So it can either form this carbocation, which is not in resonance. It's separated by an sp3 hybridized atom. Or it can form this carbocation, which is in resonance. And I'm going to show the resonance to the right. Because resonance forms don't exist in isolation. Sorry, resonance forms don't exist. Resonance forms are simply depictions of molecular orbital theory showing delocalized charge. But these resonance forms are not of equal stability. The one on the left has a more stable carbocation, but has a less substituted alkene, a less stable alkene. The resonance form on the right has a more stable alkene, a more substituted alkene, but a less stable carbocation. So if we were to show a reaction coordinate diagram for this, I have this delocalized positive charge, and I have bromide. In order to react on the right with bromide, and have my nucleophile attack this carbocation, attack the resonance form at the primary carbon, I need to have enough energy to make an unstable carbocation. But when I do that, I form a more stable alkene. On the left-hand side, if my bromide reacts with my secondary carbocation, this does not take as much energy, but it does not provide as much stability in the final product. This requires the least amount of energy, kinetic. This requires more energy, but gives more stability, thermodynamic. I remember thermodynamic more easily than kinetic because it is the most dynamic part of the reaction coordinate diagram. It has the highest highs and the lowest lows. That is the thermodynamic product. Other students of mine tell me that they remember kinetic better because it's kinetic, relates to kinesiology, relates to movement, relates to not having enough energy to really move other than the least amount of energy required. Cool, right? So when working with a conjugated diene, the carbocation that forms is a resonance stabilized carbocation. And we can actually leverage temperature to control which carbocation we attack, which alkene we produce at the end. Going up, I've shown us doing hydration. Can you tell me whether this is the thermodynamic product or the kinetic product? This is kinetic. The carbocation that reacts to form that alcohol, the carbocation is secondary as opposed to primary. Could you tell me if this is a 1,2 addition or a 1,4 addition? 1,2 addition. The hydrogen and the alcohol add adjacent to each other. The reagent that we would need, of course, is water and acid, much like our, sorry, I'm going to do that in a different color so it stands out. We need water and acid, just like we needed with our alkene, acid catalyzed hydration. But I'll admit that this was maybe just a an oversight in my part in not drawing both the kinetic and the thermodynamic product, because it is really challenging to run a reaction with water at negative 78 degrees Celsius, because famously water freezes at 0 degrees Celsius. So I would like you to predict what the 1,4 addition product would look like for this reaction. What would the thermodynamic product for the hydration of the diene look like? And add that in. Draw the thermodynamic product. Nailed it. Nice. Nice. Catching on to how the pi bond moves.
Can you explain something?
I can try.
Back in the carbocation, like those resonance structures,
Yeah.
the pi bond stayed on the terminal end in like that first option, but then it moves on the second one.
Mm-hmm.
Can you, I don't know why that's not.
Do you see in the middle where I've got the delocalized double bond and it's kind of making the semicircle? Yeah. The pi bond unfortunately, is not in either of those positions. The pi bond isn't here, and the pi bond isn't here. There's actually a molecular orbital holding these electrons that spans all three of the atoms. That's where the pi electrons are. The pi electrons are across all three of the atoms. If you're comfortable with saying that electrons can exist across two atoms, it's not a far jump to say that it can exist across three atoms. And then the nucleophile is either just attacking here or attacking here. But we can show the arrows to show the movement between resonance forms. Let's say I formed this, and I want to show the electron movement to get to this structure. This pi bond needs to break, so electrons need to move from there. This pi bond needs to form, so electrons need to flow to there. That's my arrow. That's it. That's the relation between them.
I guess that makes sense between those two, but I'm really confused how we're going from the original with the two terminal alkenes, to then that.
So that's just HX addition. Remember, the H is being taken by the base. The base is the alkene. And either of those carbons could use the electrons, but one of the carbons does not create a stable carbocation when it uses them. So that just doesn't happen. This carbocation forms, which means that this carbon has used them, which agrees with what we said back in the alkene chapter. We said a less substituted carbon is more negative, a more substituted is more positive. So this carbon is using the electrons, CH2 to CH3. I formed this carbocation, but this carbocation is in resonance.
Okay, wait. I think I know what is messing with that. It easily could have formed a resonance on that third carbon.
This alkene could have reacted.
Yes, and then it would have formed like resonance on like the other opposite side, right?
Correct.
Which is basically the same thing, just flipped.
You're exactly right.
Okay.
Yep.
That makes sense.
And there are conjugated dienes where it's far more confusing because depending on which alkene reacts, you actually get a different combination of resonance carbocations. I'll avoid giving those to you. So we'll look at these symmetric dienes where either alkene attacks, forms the same carbocation. All right, so did you guys get this? Our 1,4 addition. Notice how the pi bond has relocated. The pi bond is not where it started at either position. It's now between 2 and 3. Okay, fun? Do you have a question? Okay. Next page. Last page. Last page ever. You're not coming to OChem 2? Oh, good. You guys are all right if I erase this? Jordan, you too? Okay. What starting material do we have in the middle of this next reaction coordinate diagram? Anybody? Actually, we can't describe cis or trans on these alkenes, but are you thinking of what you got from the reading?
I don't know, actually.
Okay, because there's a term there that I do want to lean into, but it's slightly different. Anybody else? What can we use to describe this? Whether it's its name or something about it? Ooh, don't look at that. Anybody? 1,3-butadiene, perhaps, like we had here? It is, right? It's 1,3-butadiene. It's a 4-carbon chain, alkene at 1 and 3, but there is a difference between them, right? What's the difference? Well, the alkenes themselves can't even be described as cis or trans, because the alkenes both have one carbon that has two identical groups. So the alkenes are not themselves cis or trans alkenes, but they are in a different conformation. The conformation that we just looked at describes the sigma bond connecting them as S-trans. The alkenes, relative to that sigma bond, are oriented trans to each other. But here, and I drew this way too far to the left for what I need to do. Relative to the sigma bond, these alkenes are cis to each other. It's a conformational change. This is not a stereo configuration in this molecule. It's just saying if you can rotate around that bond, you go from S-trans to S-cis. And actually, it's not super easy to rotate around that bond because of the p orbitals that I described earlier. Molecular orbital theory says there is a pi bond there. You would need a lot of energy to be able to rotate around that pi bond. When a conjugated diene is in an S-cis configuration, it's able to run the Diels-Alder reaction. Those of you on Monday, I'm sorry you missed out on doing the Diels-Alder lab. It's not very, it's pretty anticlimactic. Those of you that ran it today, would you agree? Those of you running it tomorrow, heads up. It's a bit of an anticlimactic into the semester. It looks like a really cool mechanism and reaction, but you just dump it together and then they form a solid. It's very fun. The Diels-Alder reaction is named after two guys, but you should think of it as a 4+2 cycloaddition. Believe it or not, the conjugated diene is the 4 of the 4+2. So we are missing a reagent as of now that will have the 2 remaining carbons. And then, of course, cycloaddition says we'll form a ring here. And 4+2 creates what size ring? 6-membered ring. So all of our products have a 6-membered ring associated with them. And I want you to notice how each of them has a cyclohexene configuration, and then some modifications. First, I want to address that this is one of the few reactions that seems to have very standardized way of mapping the carbons. The S-cis conjugated diene is labeled atoms 1 through 4. And if you guys recall, when we did the 1,4 addition, we ended up with a similar bonding pattern where atoms 2 and 3 share this pi bond. It was 1 and 2 and 3 and 4, but now in the products, it's atoms 2 and 3. This is a really convenient way to make predictions about what the product will look like. It's a very convenient way to look at the product and dissect it and figure out what the starting materials must have been. Let's start with the simplest. In the reaction to the right, I'm going to get rid of this S-cis symbol for a little bit more clarity. This is my diene. The missing reagent is referred to as a dieneophile, something that loves a diene. And the simplest dieneophile is ethylene. Okay, it can look a little weird to draw ethylene that way, so you can draw it horizontally. or you can even add in the CH2s that are on there. And ethylene makes up carbons 5 and 6 of our cyclohexene ring. This is an addition reaction. We said that addition reactions consume pi bonds. 1, 2, 3 pi bonds, 1 pi bond. Is this a double addition reaction? Am I adding 2 sets of 2 groups? No, I'm only adding 1 set of 2 groups. I'm creating a bond to atom 1, and I'm creating a bond to atom 4. That's all that I'm adding. That's a normal addition reaction. But why then have I consumed 2 pi bonds? Well, one of them here has been converted into the ring. So I've created a ring, and that has replaced one of my pi bonds. I still have gone from 3 degrees of unsaturation to 2 degrees of unsaturation. 1 degree of unsaturation consumed. All right. That's our simplest. But a lot of these Diels-Alder reactions are improved. The activation energy is lowered when the dienophile has groups added to it that have strong electronegativity, especially conjugated electronegative atoms, an uninterrupted series of p orbitals. So in the reaction going up, we introduce a reagent that has ethylene and 2 nitrile groups, 2 cyano groups. From the product, we can see that one of the nitriles is bonded to 5, one of the nitriles is bonded to 6. So I'm just going to be swapping out one of these hydrogens for a cyano group. But we can also see that their stereochemistry on the ring is different from each other, which means that their stereochemistry on the alkene is also different from each other. So a trans product comes from a trans starting material. I have trans 1,2-dicyanoethylene, which gives me trans dicyano in my cyclohexene product. In the last reaction, there's another distinction. And I've got ketones. Atoms 5 and 6 have these electronegative atoms conjugated just like our second reaction. Did I mess up? I've been known to mess up. Did I mess up and accidentally provide a pi bond between 5 and 6? I did not. Which means our starting material is not just ethylene or substituted ethylene. Because when ethylene reacts, 5 and 6 lose their pi bond. When substituted ethylene reacts, 5 and 6 lose their pi bond. So here, 5 and 6 must have lost a pi bond. So here's atom 5, here's atom 6, and an additional pi bond, an alkyne. An alkyne that has a ketone on one carbon and a ketone on the other carbon. And then when 5 and 6 react in the Diels-Alder, they give up one of their pi bonds. Very cool. Very fun. I'm not going to have you know the mechanism for this, but the mechanism is not challenging. It's actually just a circle of arrows. Carbon 4 attacks 5, carbon 6 attacks 1, carbon 2 attacks 3. So they just cycle between themselves. Carbon 4 attacks 5, carbon 6 attacks 1, carbon 2 attacks 3. I think we practiced with this back in section 6, right after the midterm, when we were doing more mechanism problems. So if you guys remember that worksheet where I gave you 1-step, 2-step, 3-step, this was one of them. Okay, Diels-Alder reaction is not that challenging, despite how complicated it might look. Have you seen this type of reaction before, especially outside of lab? Was that sarcastic, or? You haven't seen this reaction before? Oh, you've been looking at it all semester long on the front page of our Canvas site. This is a Diels-Alder reaction that I invented, and I have no idea if it can actually work. It would just require very specific chirality. For instance, in the final product, these carbons are all, or these 2 carbons are chiral, which means these 4. These 4 carbons are chiral, so these 4 carbons would need to have the right chirality. That's an intramolecular Diels-Alder reaction. The conjugated diene is actually an S-cis conformation locked as S6. S-cis. 1,3-butadiene, in theory, can rotate between S-cis and S-trans. It takes a lot of energy. But that diene can't rotate. It's stuck inside of a ring. And there's other dienes, usually that involve rings, that are locked in the S-trans configuration. And then the dienophile is on the right-hand side of the structure. And you can see it's the dienophile because it has those electron withdrawing groups, those conjugated electronegative atoms that pull electron density towards themselves. So I want to do a practice problem with you guys where we dissect a Diels-Alder product and we figure out what starting materials are needed to make it. Tricyclic product. I've got some very obvious electron withdrawing groups. Similar to the nitriles and the ketones, I've got these 2 ketones here. That's giving me a reference point of where carbons 5 and 6 might be. There's another very useful reference point in the product. 2 other atoms that I can pretty easily map to my 4 or 2. Can you tell me? The alkene is always atoms 2 and 3. So here's 2 and 3. Here's 5 and 6. Notice how 5 and 6 are the ones bonded to those electron withdrawing groups. So here's 1 and 4. This is a retrosynthesis arrow. It says, what did this come from? Can you show me? Break apart the product. show me the diene and the dienophyl. If it helps, redraw that structure and erase the bonds that form during the Diels-Alder reaction. Mm-hmm. Nailed it.
Would it have to be a ring? That one?
Well, remember, cycloaddition means that we add a ring. If I have 3 rings in my product, and I formed one because of Diels-Alder, how many do I have in my starting materials? Yeah, that makes sense, right? 2 plus 1 gives me the product of 3. Where those 2 rings show up, you'll have to decide. Can you map these? What numbers do they have? Nice. Now, these atoms also connect like this, right?
Yeah.
And these atoms connect to themselves like this. So you can kind of fill in what's missing based on what you already know is connected. Well, it's not a bad start. You can redraw the whole thing and then just erase the bonds that need to form in the product. Like consistently, we form a bond between 1 and 6 and a bond between 4 and 5. So identify that bond position and then erase it. You know, Britton, you were off. I mean, that had a component to it that was right.
I think I just went the wrong way.
Yeah.
From this side and it comes, but this is the other ring.
Yes, yes. I already gave you a thumbs up, didn't I?
Like that?
Yes, Allie. Yes, exactly.
I didn't hear the question.
We're figuring out what diene and what dienophyl made this product.
Okay.
You got it, Brenna. Gabby, you're off to the right start. You too, Layla.
There's a missing double bond there.
Well, would you say there's a missing double bond on the right? Like when we did...
Oh, because it's completed on this one. Oh.
Yeah. Did it? Does it make sense? Did I already give you that thumbs up? Good.
At least
Did you guys get it?
I don't.
Yes,
see
you
that.
did.
Okay.
Yep. So like I recommended, you could start by just redrawing it and then erasing the bonds that need to form. What bonds need to form? Well, a bond between 1 and 6 needs to form. So I'm going to exaggerate this a little bit so that it's a little bit easier for me to redraw it or to erase some bonds. We identified 1 and 2. So here's 1 and 6. That bond is something that I need to form during this process. So I'm going to erase it. You agree? 2 and 3, that pi bond needs to form during this process. 4 and 5, that bond needs to form during this reaction. 5 and 6 needed to have a double bond because a pi bond is consumed in the dienophyl. 1 and 2 need to have a bond. 3 and 4 need to have a bond. Here's how you could also solve this. You know that this reaction requires a conjugated diene and a dienophyl. So here's atoms 1, 2, 3, and 4. And I already found 2 and 3. Did you notice that 2 and 3 came back around through another ring and connected to themselves? They loop around and reconnect. And 5 and 6 do the same thing. 5 and 6 are connected to each other through another ring. And again, I've got 2 ring starting materials coming together to form a third ring in the product. Okay, those are all the reactions. You want some more? We can find some more. I'm just kidding. What I sadly ran out of time to do was the multi-step synthesis here at the end. So I'd like to show you guys how to solve one of them. I suspect maybe none of you have gone through and figured out which one you want me to solve in front of you. So I will, I'll try to decide quickly. They're all so good, so I don't know. I mean, we can do all of these in class during our review as well next week, if you'd like to. Take a stab at them, though, before you do. One thing I'm liking about these problems, they test nomenclature, too. They require you to know some of your nomenclature to be able to do it. I think I'll leave number 1 because it's probably the easiest. I'll show you how to do number 4. I think 4 is probably the hardest. 4 says, predict a plausible synthesis pathway to form 4-bromo, hexane 3-ol, from 3-hexine. This cannot be done in one step. It requires at least 2 steps to do. I think all of these were designed. No, number 2 I think requires the most steps. All the others can be done, I think, in 2 steps. Can you see it? Do you know what? I didn't put any chirality in it. If I had described the chirality of those carbons to be wedged, both wedged or both dashed or wedged and dashed, that would actually be a different story. I would have to be more specific about my pathways. But since the chirality is not specified, there's actually more than one route. I need to consume both pi bonds of the alkyne. I need to add hydrogen to both carbon of the alkyne, and I need to add bromine and alcohol to one of each carbon of the alkyne. A vicinal halohydrin. That's a functional group that we learned how to make via alkene addition reactions. So if I can take my alkyne and turn it into an alkene, I can run halohydrin addition. So how do I get my alkyne into an alkene? Partial hydrogenation. And this is where the lack of chirality at that position is making it a little bit easier, because I could use either one of my partial hydrogenation reactions to do this. If I had specified chirality, one of those 2 partial hydrogenations would be required. Since they give stereoisomer alkenes, the X2 in water addition will give stereoisomer chiral carbons. Some tips I normally give, I've run out of time. Brainstorm. Figure out what is happening, what's being changed, what's being modified, and think about reactions that you can use. Map your carbons. Figure out which carbons are changing, which carbons are being added, which carbons are being cleaved. Regiochemistry with map your carbons. And then lastly, work forward and backwards. I looked at the final product and I said, I know a reaction that gives me Br and OH vicinal to each other. And I know what starting material would be required to get me there. So I actually started by working backwards, because how many things can we do with alkynes? Like 12. So I wasn't sure what to do with the alkyne moving forward until I worked backwards, and then I was able to figure out a useful synthesis forward. These are my tips. Practice on some of the others. 1 and 3 should be very simple. 2 might be a little bit challenging. And by very simple, I mean like work at it. Unit test this weekend. The last unit test. If you'd like, we can push it to next weekend and not do a review next week. No, I'm just kidding. We're not going to do that. Unit test this weekend. I'll grade it. I'm hopeful that I can grade it Monday. I should be able to grade your Part B Monday. And then come with questions Monday to the review class. Specific questions, general questions, exam questions, unit test questions, homework questions, practice questions. Anything you got. Have a good weekend, guys. See you Monday.